Hey everyone, welcome to part 2 of 5.5, and now we are talking about compound continuous versus compound n times. We could do quarterly, monthly, yearly, bi-yearly, biannually, all sorts of different things. So if we're talking about compound continuous, that means it's continuously going, the interest is continuously going back into your account, and we're using what I call the PERT formula. That's the principal times e to the RT. Okay, so that's the PERT formula, and then I call it the compounded n times formula, where the amount equals the principal times 1 plus r over n to the n. So we want to know how is this one related to that one? How are those two things related, right? So how do we get from one to the other? Well, there's actually a proof. So I'm going to be looking here at my notes a little bit because I want to prove to you that if we make this n infinitely large, we end up with this formula. Okay, so there's a couple of things that you're going to need to know first, and this is theorem 5.15, and that's the limit with e. Alright, so we can say the limit as x approaches infinity of 1 plus 1 over x to the x is going to be the same as the limit as x approaches infinity. If I multiply, let's say we get common denominators, multiply this by x, so it's x over x, 1 over x. That's going to be x plus 1 over x to the x. And that is going to be e. That's how we actually come up with e. If you take some number, you make x really, really large. 1 plus some really tiny number to the x is going to end up being e. All right, let's kind of change this up a little bit. There we go. Okay, that's better. Now, we're going to use this. This is going to be important because we have to kind of bridge the gap. You might even be able to say, oh, this kind of looks a lot like this. So if I can kind of get this to look like this, I'm going to be able to substitute e in. Alright, so the first thing we're going to say is a equals, we're going to say, let's take this x value, let's take this n value and put it, go to infinity of p times 1 plus r over n to the n, right? Because n was just replacing x. So what we're going to do as n approaches infinity, well, that's really going to be the same as I'll write it over here. A equals, there we go. A equals, we're going to just say the principal. The principal is not going to change no matter what n is, so that's going to be the same. We're going to say the principal times the limit as n approaches infinity of 1 plus r over n to the n. And you say, okay, but now the problem is we have this r here, and this is supposed to be 1 over x, not r over n. Alright, so if I want to get this to be a 1 over something, what I can do is just make this the reciprocal, right? So I can say r over n is the same as 1 over n over r, right? Okay, so we can say a equals the principal times the limit as n approaches infinity of 1 plus 1 over n over r to the n. Now instead of writing it to the n, actually I'm going to change my marker here because this one's starting to die out on me, and I don't want to do that. I'm going to change to gray. Seems like a good color. So we have 1 over n to the r. Now what I want to do is I want to keep this as to the n, but what I'm going to do is I'm going to change that up a little bit. If I do n over r and take this whole thing to the r power. Okay, now you say, well, that's kind of weird. But if I distribute this in, r divided by r times n, the r's would cancel out and be left with just n. So I'm kind of doing a fancy way of using exponents to rewrite n in there, okay? And you'll see why I'm about to do that, because the next thing I'm going to do is I'm going to say this is the same as the principal times the limit, and what I'm going to do is I'm going to say let x equal some n over r. So I'm going to now I'm going to change my variable and say the limit as x approaches infinity, because as n gets really large, it doesn't matter what r is, it's going to go to infinity, right? So it doesn't matter what r is, because we're going to make n this really, 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 really big number, right? So we can say this is going to be the same as 1 plus 1 over x to the x, and we're going to say that to the r, right? This r stays the same. N over r is just being replaced with x. And now I look at this and I say, well, I know what this thing is. It's right here. It equals e. So I can say this is going to be the same as p times e to the r. Okay? So that means all we have to do is say, how long is that going to be? And we have the formula. Multiply by t for that many years, and you got it. So that is how we go from compound n times to to compound continuous. We have this one. As n gets really, really large, it just goes to e. All right, there you go. Now what we're going to do is let's look at a couple of examples here. Let me get set up and we'll get going. All right, so here we go. Here's an example, and it says a deposit of $2,500 is made into an account that pays an annual interest rate of 5%. Find the balance in the account at the end of 5 years if the interest is compounding quarterly, monthly, and continuously. So these are all slightly different. So what we're going to do is we're going to say for all of these, we know A equals, and I need the principal, 2,500. Okay, I know what the rate is, 5%. Remember, that's 0.05 as a number, so don't forget the 0 in there. Otherwise, you're getting 50% interest. Hey, that's a really good deal. All right, and we also know this is going to be t. All right, so if we're talking about quarterly, we're going to use that other compound formula 1. We're going to use A equals, there we go, P times 1 plus R over N to the N. Okay, so how many times is it compounded? And we're also going to actually multiply that by, in this case, T. Okay, so we don't know what the amount is, but we know that the principal, so let's do quarterly first. We're going to say the amount is going to equal 2,500 times 1 plus 0.05. And then we say divide by how many times is this compounded? Well, it's compounded quarterly, and hopefully you know that means it's going to be compounded 4 times. And then we're going to do this 4 times 5 for the number of years. So it's compounded a total of 20 times. Okay, so when we do that, you're going to get an answer, and your answer is, the answer is 3,205. So for this one, it should be 3,205, about. Okay, so I'm going to set up monthly, I'm going to set up continuously, and then we can go ahead and we can just get the answer. So the monthly is going to be very similar. A equals P parentheses 1 plus R, I'm not going to do that whole thing again, I'm not going to do R over N. It's going to be 0.05. Monthly is going to be 12 times per year, and it's going to be 5 times 12, which is 60. So it's going to be to the 60th power. Okay, so we'll be able to go through and solve that one. So then, continuously, the amount is going to equal P times E to the rate, which is 0.05, times the time, which is 5. All right, so we're going to go through, and we're just going to find these answers real quick, and here they are. All right, so we have those, and the answer should be right above me up here. And so if you look at, if we do it monthly, it's $3,208.40, and if you compound continuous, $3,210. So it's a difference of about $2 here, and the other one was $3,205. So you see, compound continuous is going to give you a little bit more money, and if you're doing this for more than 5, you're doing it for 10, 20, 30, 50, 80 years, something like that, it's going to really start to add up. So compounding continuously is going to be the way to go. All right, so then what we have is, here is one more. I'm a little bit in the way. Let's see if we can move me maybe over here. Does that seem okay? Oh, I'm gone. There I am. Okay, so bacterial culture is growing, and the logistical growth function, I'm going to write it out because it's annoying to type in Word. The logistical function is y equals, we have 1.25 divided by 1 plus 0.25 e to the negative 0.4 t, where t has got to be greater than or equal to 0 because t is time, so t can't be a negative number. Okay, good. So we want to find the weight, which means we really want to find y after 0 hours. So we put in 0 in for t. E to the 0, anything to 0 power is going to be 1, so that means this is going to be 1. So after 0 hours, it should just be 1, and our unit is in what? It's in grams, so we can say that's 1 gram. Okay, so in this case, 1 hour, 10 hours. What happens as the limit goes to infinity? So we're going to say is we put in 1, we put in 10, we put in this one. So I will just tell you the answers for these, that way you can go through, put in 1 for t, figure it out. Put in 10 for t. When you put in 1, it should be about 1.071 grams, so not much. At 10, it's 1.244 grams. So what do you think is going to happen as t approaches infinity? Well, t is going to approach infinity. T is going to approach a really large number multiplied by a negative. So that's going to be a very large negative. So you say e goes to the negative. Well, what happens when e goes to a negative number? When this whole thing is negative, which means you're going this, nope, you're going this way, right? You're going to the right on the graph. So if you think about it, when you think about the e graph, maybe we can just graph this real quick. If I go to e to the x. This is what this graph looks like. We're saying go all the way this way. What's that number really going to be? Well, it's really going to end up being 0. It's going to go really, really close to 0. So the limit as e approaches negative infinity is going to be 0. So that whole thing is 0. So really it's going to be 1.25 over 1 plus 0, which means it's going to be 1.25 grams. And you can tell that after even 10 hours it's getting pretty close. All right. So there you go. That is the assignment. That is all the examples that I have for you. And you have all the interest formulas that you need. Good luck.